So now we're at our last step. We are adding more than the acid, so more base than the initial acid. And as always, we're just going to do this even though you should already have this number once you do it the first time. You don't have to keep redoing this math. But what we found was we had 0.006 moles of HA. Now we have to calculate for the OH minus. And so 0.065 liters, because we convert the milliliters to liters, times 0.100 equals 0.0065 moles of OH minus. And if we do the math, what's happening here is we are starting with HA and we are adding OH minus. We're going to get A minus and H2O. We're starting with 0.006 here, 0.0065 here, none of that. This time our limiting reagent is our HA. So we're going to subtract all of the HA and we're going to add it to the other side. And what we find is we have no HA. We're going to have 0.0005 moles of OH minus, and we're going to have 0.006 A minus. Because we have excess hydroxide, and that is a strong base, we can ignore the weak base, the conjugate base, and only focus on the OH minus. Because it's in excess, we can just take the concentration of that OH minus and convert it directly to POH using negative log of its concentration. Before we do that, though, we need to take the moles of my hydroxide divided by the total volume, which is 0.105, the 65 plus 40 milliliters, 105 milliliters or 0.105 liters. And we get a concentration equal to, let's see here, 0.00476 molar. What do we do with that number? Well, that is the hydroxide concentration. So we need to convert that to POH and then pH. And so we take negative log of 0.00476 molar to get POH, which ends up being, let's see here, negative log 0.00476, 2.32. To find the pH, 14 equals pH plus POH. So pH is 14 minus 2.32, and the pH is 11.68. So in summary, what we do is when we do a titration, starting with the weak acid and titrating with a strong base, we are going to first do no KOH added, typically. If we don't add any base, and it could be NaOH as well. If we don't add any strong base, we just do the Rice table for Ka, where Ka equals x squared over the initial concentration of the acid. If you start adding KOH or the base, you want to figure out the moles of each. As long as you don't make it to the equivalence point, you can do the Henderson-Hasselbalch equation, keeping in mind any hydroxide added is going to be converted to A minus, and we need to subtract that from the initial HA, or the acid to begin with, to get the new HA value. There's a special scenario halfway to the equivalence point where the pH equals the pKa. Once we reach the equivalence point, what we need to do is another Rice table, but now we're dealing with the conjugate base A minus, and we have to flip Ka to Kb. And when we solve for the concentration, it's actually the hydroxide. So we have to solve for POH and then convert to pH. Last is going beyond the equivalence point. At this point, the equilibrium is not important because we have an excess strong base. You figure out how much strong base is in excess, you convert it to concentration, and then you find the POH, then convert to pH. If you were to start with a weak base and titrate with a strong acid, the steps would be the same, but you're flipping the calculations. You're starting with Kb before you get to the equivalence point. At the equivalence point, you now have Ka. And initially, you're solving for hydroxide concentration, then converting to pH. And after the equivalence point and at the equivalence point, you're solving for H plus to solve for pH directly. So the calculations are essentially the same whether you're titrating a weak acid with a strong base or a weak base with a strong acid. You're just flipping whether you're starting with the hydroxide or hydronium, the Kb or the Ka first. I hope these videos helped. And again, if you have any questions, feel free to reach out. I can always try to make more videos explaining similar problems.